So now that we know what the E1 mechanism looks like, the unimolecular elimination mechanism, let's take a look at an example where we have a huge mixture of products that are formed here and see if we can come up with a mechanism for it. Okay, and a mechanism that involves perhaps something interesting that we get with anytime we have a carbocation, we have to be aware that we might be having some carbocation rearrangements possible. So let's take a look at these. So notice we're getting a mixture of substitution and elimination products. Somewhere a nucleophile has replaced the leaving group, substituted for the leaving group, and others where we've had an elimination, meaning we form an alkene product. So of the elimination products shown below, which is expected to be major? So let's ask that question first. So of these three alkene products, how would we pick the major product? The major product is going to follow Zaitsev's rule, meaning it's going to be the most stable alkene possible. So what's the difference in these three alkenes in terms of their stability? Remember, the more substituted alkene is always going to be the most stable. So we have one that is tetra-substituted. It has all four positions of the double bond. All four substituents are carbon groups, so that's going to be the most stable. So D is going to be the major product of all the alkenes, and that's because it's tetra-substituted. Tetra-substituted, and that makes it the most stable. Remember, we described that as Zaitsev's rule, and that's almost always what we expect for alkenes. The only exception to that is when we're doing an E2 with a strong bulky base like T-butoxide. Every other case, we're going to always try and get the most stable alkene possible. And what mechanism accounts for the alcohol product? So we call it an alcohol when we have an OH on a carbon chain. So that's referring to A and B. It's asking what mechanism do we use for that, and what mechanism do we expect for the alkene product? So how do we predict a mechanism? We need to now look at our reaction conditions. We see water as our reactive species that's doing the substitution, the elimination. So what do you think about water? Acid base, electrophile, nucleophile. Is it a strong nucleophile? Is it a strong base? Remember, this is not ionic. So I don't have hydroxide here. I have molecular stable neutral water. And so water is simply a weak nucleophile and a weak base. So we're not expecting our bimolecular reaction. So that means we can't do Sn2. We can't do E2. Bimolecular means there's an attack. There's an attack to do backside attack or attack on that beta proton. So instead, what's going to happen with a weak nucleophile base? That's when we expect a carbocation. Carbocation are unimolecular reactions. So in other words, we're expecting the Sn1 to be the mechanism for our substitution products and the E1 to be the mechanism for our elimination products. Okay, in other words, carbocation formation. So then we're asked to provide a mechanism that accounts for all the products shown. So how do both of these reactions start? What do they have in common? What's happening here? They are involving a carbocation intermediate. So because I don't have a strong nucleophile, a strong base, my leaving group is going to just leave on its own. My leaving group just leaves on its own. And so that gives a carbocation. And how can that lead to product A? How can that lead to product A? That is a substitution reaction. So that means water is going to act as a nucleophile, a weak nucleophile, right? But it's strong enough to attack a really reactive carbocation, which is a very strong electrophile. And so that reaction definitely can happen. So water comes in and attacks. So this oxygen now still has two hydrogens on it and a lone pair. So this doesn't look like a neutral oxygen. And so let's count up for our formal charge. 1, 2, 3, 4, 5. oxygen wants 6. So this is an O+, it's missing an electron. So I did my substitution, but it's not a neutral product yet. So how do I get to A? How do I get to A? I need to deprotonate as my final step. So I could use water again as a base to deprotonate the intermediate, the oxonium intermediate. So this is our usual 3 steps that we saw for solvolysis, reaction with the solvent, form the carbocation, nucleophilic attack, and then deprotonate to give the neutral product. Okay, so that is, we can show our reversible step here. Chloride could leave, and we get this carbocation. Okay, so that accounts for A. And how do we get to B? How do we get to B? Well, this now is having the alcohol at a different carbon. The way we could get to a different carbon is we can have a rearrangement. So what's going to happen is, and this is actually a favorable rearrangement, what's going to happen is we're going to get the positive charge on this position. Notice this has, I'm sorry, this has the same carbon skeleton as product B. So, so how does this rearrangement take place? This is described as a methyl shift, And this is a carbocation rearrangement. It's going to rearrange, and sometimes I use a little symbol here to kind of be a quick note to myself that I've done a rearrangement. And what does that look like? This methyl group, just with its two electrons, is going to move from one carbon to the next. So this CH3 group, if you want to draw it in, just to highlight it, this CH3 group picks up and moves. And so now it's attached to the next carbon over. And then this carbon, which had 4 bonds, now has just 3 bonds. And so that makes it a carbocation. So why is this such a favorable rearrangement? Because I went from a secondary carbocation to a tertiary carbocation, and this is more stable. So I would expect this to account for quite a bit of product. Notice I haven't shown the reaction yields here. I haven't asked for explanations, just wanted to throw that in there to remind you that that's the driving force for the carbocation rearrangement. Okay, so now I have the carbocation in the correct position, and so that is my super duper electrophile, super duper very reactive electrophile. So water's coming in as my nucleophile, and it's now attacking at this tertiary center, just a single arrow to show nucleophilic attack. And once again, that oxygen still has its 2 hydrogen atoms with it, still has its 2 protons. So this is still once again, going to lead to an oxonium ion. So that's not my final product. And so the way I get to my final product, to get to B, let me see how much room I have here. Am I doing okay? I'll go this way. To get to B is to deprotonate the oxygen to get a neutral oxygen. So now I have an OH at that position, a neutral OH. So those are my 2 substitution products. Those both came from an Sn1 mechanism. Sn1 mechanism. Carbocation. Okay, so how do I do my E1? These next 3 are all going to be from an E1 mechanism. So I get the same carbocation. We have 2 carbocations now. Sorry, we have 2 carbocations. We have the secondary carbocation and the tertiary carbocation, and either one of those, are going to be used to get to C or D or E products. So we could just go ahead and redraw. So we're looking at different pathways. So water can attack the secondary carbocation, right? Or it can rearrange. So we're kind of showing the same carbocation doing some different pathways. So same thing here when we're at this carbocation. This can, instead of rearranging, it can just eliminate to form a double bond in that position. That is product E. Nope, it's not. Sorry. That is none of these products. All these are from the rearranged product. I'm sorry, I didn't look close enough at my carbon structure. Notice that all alkenes have the same carbon structure, so this makes sense. This is actually what I would predict because the tertiary carbocation is more stable. Okay, so okay, actually I had two products here. I just realized I have a typo. Sorry, I need to correct my notes. Oh my goodness. I did have one. Because D and E as drawn are the exact same product. So that's not very helpful. D and E are the exact same product. My apologies. Okay, so so that would have come from this first carbocation. Let's redraw. We could just draw this as another path. So this secondary carbocation can go to product E, the revised product E, and how does that happen? Well, I could just deprotonate. The way you form an alkene from a carbocation is I use water as a base to deprotonate the beta hydrogen. And so now I can get an alkene there. Okay, so but D and C and D both come from the tertiary carbocation, So why can I get two different alkenes here? Because I can use this as my beta proton, or I can use this as my beta proton. Those would give my two different alkenes. So product C uses the proton on the end here. And so again, water as my base, two curved arrows for every proton transfer. Right there. So that is product C. And another option is to go to the more substituted position. That, of course, would be the better deprotonation to take place because that would give us a more stable alkene. So that is always our goal, and that actually will be the major product in terms of the alkenes. We would expect that to be formed to a larger extent because it gives a more stable alkene. So water coming in and deprotonating this position and forming the double bond in the middle carbons gives the tetrasubstitute alkene, which we said of the alkenes, that's going to be the major. So this is how we get to all 5 of our products, and we're going to very often get mixtures like this. So this is great practice. Make sure that you know how to form a carbocation when you expect carbocation reaction conditions, because we have weak nucleophiles, weak bases, and then recognizing that sometimes carbocations rearrange. So as a result of both the rearrangement and the fact that it's a carbocation means I have a huge mixture here of both substitution mechanisms from the products from the Sn1 mechanism and elimination products from the E1 mechanism. All right, thanks for listening.